Okay, so let's begin with the binomial distribution. And again, the basic idea is that we try to find the probability of getting X successes in N trials when the success probability is P. So the standard example is like you flip a coin 10 times and you want to know what's the probability that you get exactly 3 heads or 4 heads or 6 tails. The binomial distribution has an underlying process which is known as a Bernoulli process, named after Daniel Bernoulli. And that basically says that the binomial distribution is a discrete probability distribution. So again, discrete means we are dealing with counts, not with measurements. And so that Bernoulli process, it's applicable to decision-making situation in which a sampling process conforms to a Bernoulli process. That's what a binomial distribution is. And specifically, a Bernoulli process is subject to the following assumptions. First, we have 2 mutually exclusive events. We typically call them success or failure. And the outcome in the series of trials or observations, they constitute independent events. So it's basically drawing with replacement. So if you go back to that example of coin flips, if I have like a head in the first flip, that doesn't mean I take away any heads in subsequent flips. So the events are independent, and the way you can think about it is drawing with replacement. And also the probability of success in each trial, which we call P, that remains constant from trial to trial. So that is said that the process is stationary. So again, coming back to that example of a coin flip, if I flip a coin 1,000,000 times, at the 1,000,000th time, the probability that I get a head or tail is still 50-50. So that is a Bernoulli process. So 2 mutually exclusive outcomes, they are called success and failures, and the events are independent. So it's basically drawing with replacement, and the success probability stays constant. So normally I don't really like to show you that many formulas because admittedly some of the formulas get more complicated, but the binomial distribution formula, that still has a little bit of intuition to it that we already know. And it is given by that formula that you see here. So it'll say the probability of X successes in N trials when the success probability P is a certain probability. And then the formula includes here the formula for combinations. So if you remember, N, C, X, or sometimes we wrote R, that is the formula for combinations, which can be written as N factorial over, since we choose X, it would be X factorial times N minus R factorial. That's the formula for combination. So we have already seen that. In words, what that gives you is the ways of obtaining a certain sample. So how many ways are there to obtain a certain number of events? Or what's the probability of obtaining a certain sequence? And maybe not a sequence because that would be a permutation, but what's the probability of obtaining, well, X successes in N trials? So that would be correct. So let's just start with a very simple example that we can that we basically can prove by pure logic. Let's say I flip a coin 3 times. So example, 3 coin flips. So you want to know what's the probability that you get 2 heads. So now we would write what's the probability that you get 2 successes, and the success is now a head, so 2, in 3 trials, n equals 3, if the success probability is 0.5. So now this part of the formula here, this n choose x formula, that tells you how many ways are there to get 2 heads in 3 coin flips. Well, we know that we can get 3 heads in 3 coin flips. So the relevant set would be, well, I can get head, head, tail. Or I can get head, tail, head. Or I can get tail, head, head. So there are only 3 ways of getting 2 heads in 3 coin tosses. So now let's double check with that formula. So now we have 3, choose 2, from 3 choose 2, so that would be 3 factorial, 3 times 2 times 1, over x factorial, 2 times 1, times 3 minus 2, 1 factorial. So we get 3. Okay, so it's basically 3 ways of obtaining 2 heads if you flip a coin 3 times. So that is the first term. So this is this term here. So we already know that formula. And then we just multiply the number of ways of obtaining n successes in n trials with the success probability p. So that here is the success probability p. Which in our case of a coin flip, of course, is 1 over 2, and we raise that to the number of successes. And then we also still multiply it by the number, by the failure probability raised to the number of failures. So this is the failure probability, which is also 1 failure probability, which is also 1/2. So the failure probability is also 1/2, and we raise that to the number of failures, which is n minus x. So now in this case we get the probability of 3 times 1 over 2 squared times 1 over 2, well, raised to the 1. So that is 3 times 1/4 times 1/2, which is 3 out of 8. So there are 3, there's a probability of 3 out of 8 that you can get 2 heads in 3 coin tosses. And of course the 8 comes from flipping a coin 3 times, so there are in total 8 ways of getting some results of head and tails. It could be head, 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 tail, head. So this is basically another way to look at it, is like 2 raised to the 3. Okay, so anyhow, so the formula still has many things in it that we already know. So again, the binomial distribution can be used to determine the probability of obtaining a designated number of successes in a Bernoulli process. X is the designated number of successes. So in our example, we want to get 2 heads. N is the number of trials or observations. And P is the probability of success in each trial, and Q, sometimes 1 minus P is also written as Q, is the failure probability. So you need the success probability and the failure probability. Okay, so now we do again a similar example. So let's assume what's the probability of having 2 girls when having 3 children. So how many ways are there of having 3 children? Well, it's basically, you can always have a boy or a girl, so it's 2 raised to the 3. So here, if you look at this graph, 2 times 2 times 2, that gives us 8 ways of having 3 children. We can have girl, 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 boy, girl, boy, girl, girl, boy, 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 girl, girl, boy, girl, boy, 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 girl, boy, boy, boy. Okay, so now what's the probability that we want to have 2 girls? So it's the same as with in the previous example. So when we use the formula, we would write the probability of 2 successes. So a success in this case is having a girl. When you have 3 children, n is 3. And let's assume the success probability is 50-50, so 0.5 roughly. Actually, girls have a slightly higher probability, but let's just assume it's 0.5. So then it is again the same thing. So we first use the formula for combinations. From 3, choose 2. And we already know that is 3, because it's girl, girl, boy, that's the first. Then we have girl, boy, girl, that was the second. And we have boy, girl, girl, that is the third way. So here we have 3, and then we have again 1 over 2 raised to the 2 times 1 over 2 raised to the 1, and we get again 3 over 8. So it's basically the same probability in a different context. So when it comes to calculating probabilities, we sometimes want to know what's the probability of having exactly 2 girls when you have 3 children. But sometimes you want to know cumulatively what's the probability that you have cumulatively up to 2 girls. And that means, when we say cumulatively, that means, you know, what's the probability of having no girl plus the probability of having 1 girl plus the probability of having 2 girls. So that will be cumulatively. So before we go into this example, let's quickly stay with the example of the previous scenario of the 3 girls. And let's say we want to know what's the probability of having cumulatively up to 2 girls in n equals 3 trials when the success probability is still 0.5. And that is now cumulatively the probability that you get 0 in 3 trials. And we know what that is. So that means that, so getting not a single, not getting a single girl, that is 1/2 times 1/2 times 1/2, or 1 over 8. So then what's the probability of getting exactly 1 girl? So what's the probability of getting exactly one girl? Well, there are again 3 ways of having exactly one girl. The first way is girl, boy, boy. The second one is boy, girl, boy. And the third way is boy, boy, girl. And we know that this is 3/8. And the probability of having exactly 2 girls from 3 well, if having exactly 2 girls, that is the same probability of having exactly 1 boy, that is also 3/3. So cumulatively, we will get here, what's the probability of getting up to 2 girls? That would be 1/8 plus 3/8 plus 3/8, which is 7/8. Okay, so this is the idea. So now we have here another example. What's the probability of getting no more than 3 heads in 6 tosses of a fair coin? So now we would write what's the probability of getting no more than 3 heads in 6 trials, when the success probability is 0.5. Okay, so now we would basically sum up the probability that you have 0 heads, 1 head, 2, and again 3. And the probability would be 0.656. So actually, let me already open Excel and let's introduce the formula. So the formula that you want to use in Excel is equal to binom dist, equals binom dot dist. And then you see it's pretty straightforward. It tells you what's the number of successes. So let's stay to the example. What's the probability that you get exactly 2 girls when you have 3 children? So the number of successes would be 2, comma, the number of trials, well, 3. So now what's the success probability? 0.5. And then Excel wants to know, is it cumulative or exactly? So if you want to know exactly what's the probability of getting exactly 2 girls, we would say 0 or false. 0 is false. So I can write it like this, and now we should get 3/8, which is 0.375. So that is equal to 3/8. So that is exactly getting 2 girls if you have 3 children, 37.5%. And you see, instead of a 0, I could have written false. It's the same thing. Okay, so, but if I had said true or 1, then we should get 7/8. Because that's cumulatively the probability of getting no girl, 1 girl, or 2 girls. And you see, we have to sum it up because I said no girl, or 1 girl, or 2 girls, and you probably still remember the addition rule for such events. So now we should get 7/8. So it's 0.875. Let's double check. 7 divided by 8. 0.875. So that is cumulatively. So this is how we use Excel. Okay, so back in the days when I was still a student, we worked with tables. I just want to show it to you. You don't really use them anymore, but I don't know, maybe you might see them. So here we have a cumulative binomial distribution table. And you see there is some information here, and those tables can be several pages long. So we have here the probability, 0.01, and those are standard probabilities. So we were dealing with a probability of 0.5. And then we had 3 trials. And we wanted to know what's the probability of 2 successes. So we would have to look up the value in that table, which is 0.875. And we can also use the cumulative table to determine the probability of getting exactly 2 girls. And if you remember, that was 0.375. So the probability that we had exactly 2 successes in 3 trials when the probability was 0.5, and it was not cumulatively, so in Excel language that was a 0, that was 0.375, not cumulatively. So we can also calculate that from this table, and you can see this would be exactly the difference. So between the 0.5 and the 0.875. So the probability of x equals 2 can also be written as the probability of cumulatively x is less than or equal to 2. Okay, p equals n equals 3, I forgot. So again, that's cumulatively. You can see that from the less than or equal sign minus the probability of x cumulatively less than 1 so that will give you exactly the probability of x equals 2. And you can see if you do 0.875 minus 0.5, we get 0.375. Anyhow, I will not use those tables too often because we're like in the 21st century and we can use Excel, and again the formula is binom.dist, but you may have, you should have seen such tables. Okay, so now we can use the probability, the binomial distribution, in order to visualize various distributions depending on the number of trials and and depending on certain success probabilities. And you see here some examples, and I will replicate them quickly in Excel, where we just can play around a little bit with the binomial distribution, and we can look at the normal probability distribution, but also the cumulative distribution. But I will do that in Excel, and I'll just stop here and do the next video in Excel.